So this is called free scalar field. So M will be Rn, or like you will see, sometimes it will be more convenient to say it is Rn plus 1. So V is equal to R. So as we already said, so scalar field means this. And now, you see, in our discussion in the beginning, we said that sometimes we choose our space M and we choose our space V, and we give some geometric structure to M. So let's give some simple geometric structure to M. Choose a metric on M. So let me write it in the following way. So d s square is equal sum ij, gij, dxi, dxj. So that's the local coordinate presentation of a metric on my space-time. So so let me use the following funny notation. Let me denote Gij by definition. That's the inverse. So the inverse, the inverse matrix when I write the indices up there. And so let's define L of phi di phi to be equal to 1/2 sum over ij, gij, di phi, dj phi minus 1/2 m square phi square, where m is a real valued parameter. So this metric may, in principle, depend on coordinates, even though in our examples today it will not depend on coordinates. So you see here we take some geometric structure, and that's typical of how quantum field theory or classical field theory is used to study geometry or to study topology. So you take your geometric structure and now you want to load it into your field theory. So for instance here, so this Lagrangian, this polynomial, it explicitly depends on the structure, right? So we hope that whatever we get from our classical and quantum field theory will depend on this structure, and maybe it can tell us something interesting about this structure. So that's the whole idea. Of course, that's a very simple and naive example, but in principle, that's the whole paradigm of using geometry, using quantum field theory in geometry and topology. So let's see what happens with the Lagrange equations. Right. So let me recall again. So what I should do, I should take dl over d phi, which will be now minus m square phi. So minus sum over I and j, I assume, right? There will be this derivative di. Here will be g ij. So I take the derivative with respect to this guy. I get that guy, and so this should be equal to 0. So before we give concrete examples of G, maybe some more comments. So you see here there was also a word free. So free means the following. We're looking at the polynomial L, and it's a polynomial in many variables. And if this polynomial is at most quadratic in its variables, then we call this theory free. So that's just a definition. So free L is at most quadratic. Now it is quadratic with respect to phi and gi phi, so it's a free theory. So perhaps here you will notice that since it is at most quadratic in its variables, and here we are taking derivatives in its variables, the Euler-Lagrange equations are linear differential equations. So these are linear partial differential equations. Now two sub-examples. So let's put, so m we discuss later on, but let's for a moment put m equals 0. And let's choose G just equal to the unit matrix. So Gij is a Kronecker delta. So in this case, what do we have here? So the Euler-Lagrange equations would read minus the Laplace operator of phi is equal to 0, where so this is right. So we're getting our beloved Laplace equation as the Euler-Lagrange equation. Of course, another famous example is to take G to be a constant diagonal matrix with one eigenvalue which is, say, positive and all the others negative, or the other way around. So, and here it is convenient to have it on Rn plus 1, and to align with the physics notation, we will say that the coordinates are numbered from 0 to n. So then what happens to our equation? Maybe I change the sign, so it will be d0 square phi minus sum, or maybe I write it this way, minus sum from 1 to n di square phi is equal to 0. And so this is also a very famous equation in physics and mathematical physics and in the theory of PDEs. So what's the name of this equation? Right, that's the Laplace equation. What's this equation? Wave. Yeah, so that's the wave equation. So that's the wave equation. Right. Maybe just for your information, let me also write down here the operator A phi that you can easily calculate. So here the operator A phi will be minus Laplacian. And it is independent of phi, right? Recall that we take the second variational derivative. Our series is free, so Lagrangian is quadratic. So when you take a second derivative, all the phi dependence will in general disappear. So that's another nice feature of those free theories. Typically, those operators, say phi, that we obtain, those differential operators, they are independent. They don't have any trace of the solution of the Euler Lagrange equations. And here, I think a phi will be minus Laplacian plus the 0 square. So just the operator that you see here. Right. All right. So now let me use the rest of this hour to return to our first calculations and do it from a little bit more differential geometric viewpoint. So I think that's not the last step that we take in this direction, but that's at least the first step. So let me tell you or recall a little bit so some small things on differential geometry of those mapping spaces. So let me say a little bit on that. So F, recall that's the space of maps from M to V. So let's first assume that V is a vector space. So then such a map, phi is a map from a manifold to a vector space. And here we have, let me draw the image. So that's the image of M. So we would like to say what's the tangent space to F at the point phi. So what is it? So if you imagine a one parameter family of maps, so then the image gonna move, right? So you take a point here, x, it is moved to the point phi of x, and now there will be a parameter t. So you differentiate it with respect to t, you obtain a tangent vector at this point. So d phi t of x over dt, it lives at a tangent vector here, at a tangent space here, but if V is a vector space, it is simply an element of V, right? So if V is a vector space, then the tangent space here is reasonably defined just in the same way, right? So this was a vector space, the tangent space is a vector space, and you give a tangent, so this velocity vector at every point. Now suppose that V is a manifold. So then, how it's going to look like? So here there is this manifold V. We again have the image. So here there is a point M, x. It is mapped to the point phi of x. And we're going to have this tangent vector. So d phi t of x over dt, which now lives in the tangent space to phi of x of v, right? So the way to deal with it is as follows. You take a tangent bundle of V, and you pull it back by the map phi. Right? So you consider phi star of the tangent bundle of V. So then what does it do for you? So the space where this vector lives, it gets transported to here. So you get a vector bundle whose fiber over x is exactly this space that you want, right? So T phi of f is then becomes identified with a space of sections over M of this pullback bundle. So a section of such a bundle means to a point x you associate a vector there, and the vector there is a vector where? Is a vector exactly in the vector space you want. So this means once you're given such a section, you can meaningfully write this equation. So if you have a section, let's say V here, so then you can meaningfully write such an equation, and that's what you want for the tangent space. Right. Perhaps one remark that will be important for us later, and it's also important in the I think in problem 4 of the problem set. So there is a natural action of functions on M on this C phi f. And that's just because those tangent vectors to our space of maps, to our space of fields, they are sections of some bundle over M. Here and V here. So here FV is simply mapped to F times V. Maybe a little bit of generalities on differential forms on F. So we'll, in a second, work with some very concrete differential forms, but just in general, how should we think about it? Or maybe even better say on, differential forms on F. Right. So let's go back to this diagram. So we have M times F, which is maps from M to V. We have the evaluation map, and we have the two projections. So, so first of all, let's do the following construction. Let's choose a form, say a K form on M, and let's choose an L form on V. And let's consider the pullback of alpha. So this will be a form on M. Wedge the pullback of beta. So this will be a form on this whole thing. And now assume again that the pi star, that the integration works well. Either because we chose the forms well, or maybe M is compact. Let's assume that the push forward, that the integration map is well defined. Right? That's a little bit like the things you were doing at this introductory week before the master class. So this is some kind of product, and you're taking a fiber integral, right? So this is a direct product, and you're taking a fiber integral over M. So this will be a differential form of degree k plus L minus n, where n is a dimension of M on the space of fields. So this is one of the constructions how people build differential forms on the space of fields. So I'll introduce a little bit more notation, and I will say one word on how you can perhaps understand it in a little bit more mathematical fashion. So this is, I'm not sure there is a standard notation. Let me denote it alpha star beta. And this is one of the standard constructions how you build forms on the space of maps. So notation. Since we're going to work a lot with this kind of product, perhaps it's good to introduce some somewhat special notation for the parts of the Theorem differential on this space. So let's say D is a Theorem on M, and suggestively let's denote by delta the Theorem operator on the space of fields. So the Theorem operator on F. Of course, the total Theorem operator on M wedge F, that's the sum of the partial Theorem operators. And by convention, d delta plus delta d is 0, right? Because these are odd objects. I split my Theorem operator into two parts. Perhaps just to give one example, let's take this evaluation map to build functions. So phi of x, let's say x phi in M cross M is mapped to phi of x, and one can view this phi of x as a map. So zero form on M cross F with values in V, right? So this is just tautologically, this evaluation map gives you such a function. Now you can apply each of these differentials to it. So you have d phi of x, and this is equal to some OI from 1 to n d phi over dxi, and this is a one form on this space. In fact, you can introduce a bi-grading. We can keep note of the grading on M and of the grading on F, right? So we can say that this is a 1,0 form on M cross F with values in V. So this is a bi-degree which keeps track of, so this is a degree on M, and that's the degree on F. Well, in a similar fashion, we can look at d phi of x. Sorry, here it will be somewhat more complicated. So this will be a 1, 0 form. 1, 0 form on this space. And well, here we're using this mysterious de Rham differential on this infinite dimensional space F. Here, strictly speaking, one would need to develop some theory to make it well defined, right? So what I'm doing now is very, very sloppy. But let me give you just one of the ideas how this may work. So there are many ways how you can make sense of it. So one of the ways, let me just show you the direction, is as follows. Consider the maps of subsets of Rn with arbitrary n to F. So this would mean that how such a map would look like. So you would have phi, which depends on x1, xn. And this map phi itself, it depends on capital N parameters on this space, right? So I would consider families of maps from M to V, with family parameterized, let's say, by some neighborhood of 0 in Rn. So there will be those extra parameters. So let me call this map Y, right? So the map Y maps this domain into F, and the result is a family of fields, right? So this d phi is supposed to be a form of M cross F. Now we can map here this U with the map Y, and we can ask what's the pullback of it. Now I say by definition, so delta phi is defined as an object such that for any such a map Y, the answer will be sum over J from 1 to capital N, d phi over dyj, dyj. And that's one of the strategies. You say that you never define such an object, but you define its pullbacks to all the sufficiently nice and smooth maps from all the finite dimensional domains to this space. And then you say how the pullbacks behave. Then, of course, you have to figure out what if you first map one domain to the other domain and then to F. Then they should all be consistent. So that's one way how, in principle, one can make sense of it. So there are also other more direct ways, especially as here this is a vector space, then one can also define it more directly. But that's one of the ways how, if you want, you can think about those differentials that I'm introducing. So for any finite dimensional map, in particular for any curve, for anything reasonable you map to F, you define it in this way. So, but that's just a hint on how, in principle, the differential calculus can be developed. Now, let me go back to classical field theorem. So I would like to rediscuss the calculation that we made. And for that, recall that I already introduced this curly L, which is L of phi d phi dnx. Now I'm saying, what is it actually? Well, it's a zero-end form on M cross F, right? Now, if M is oriented, and the projection pi is sufficiently nice, S is a push forward of L with respect to this pi map, so the integration map, and this is omega 0 in omega 0. So this is a function on F. Now, what about the calculation that we were making, this variational calculus? Well, so we want to look for critical points or critical maps of S. And for that, we want to take its Theorem differential. So now delta, so that's how we arranged our notations. Now delta is the Theorem differential on S. So we want to compute its Theorem differential. So this is the Theorem differential of pi star L. And how is it? When you compute them, there might be some sign, right? So this is some kind of whatever, plus or minus pi star delta L. Now let's look at our calculation, and let's try to reinterpret it from this perspective. So we're taking delta L, and we're writing it as dl over d phi delta phi. See, that's where that's why we had to discuss this form, right? So there is this form, rather tricky object, this form delta phi. So L consists of a polynomial which depends on phi and d phi, and it has this n form part. So that's what we get here, right? That's roughly the same computation that we had before. So, and here we have delta di phi, and here dnx. Well, delta di phi, that's the same as di delta phi. So here there is no difference. Why is that? Remember that this delta phi, what is it? This is a differential with respect to some other variables, right? Roughly speaking. So this means that if you have just a partial derivative with respect to the x variable, it commutes with the partial derivatives with respect to those, whatever, hidden y variables. Now, what happens next? What does it mean, this integration by parts in this language? In fact, it's the following trick. So I say that delta L is equal to delta L minus the m Theorem differential of something plus the Theorem differential of something, where gamma is the following expression. Sorry, here was some, right? So this is sum of I from 1 to n. And let me try to write it correctly. Delta phi. And well, let me see. I hope my signs are more or less correct. Minus 1 to the I, and here dx1, dxn with dxi taken away. Usually they put a hat over it, meaning that it's taken away, but on the blackboard I think I can just do like that. So there is no dxi in this product. Of course, this equality holds true for any gamma. So there is no doubt about it. Now, what is this delta L minus d gamma? So the claim is as follows. So this d, it will hit either this term or it will hit that term. So the claim is that if d hits that term, then you exactly kill this expression there. But if d hits this term, so the claim is that what you get is dl over d phi minus what you want. Sorry. di, dl, di phi So what do you think about signs? Could it be correct? My reasoning is as follows. So when you hit it with so d hits this guy, it gives you a derivative with respect to di, and it gives you dxi. So the dxi commutes through delta phi and through I minus 1 dx's to find its place. So it kills the minus 1 to the I. And when you differentiate this expression with respect to other x variables, then it gets killed because you already have a dx, all the other dx's. So I think that's the correct. So that's the correct expression. So you see, now the idea is so this is actually equal to q phi d2 phi delta phi dnx. Right? So this expression, so we split this differential of the Lagrangian form into something which defines the Euler-Lagrange equations, and in the Theorem differential of something. So remember, there were all those terms that we wanted to die on some boundaries. Now this pi star, that's an integral over m. If m has boundaries or it has infinities, then there will be contributions from the integration of this exact form at these infinities or boundaries. And typically we want it to be 0, but not all the time. So in any event, so that's the kind of next level of this. So that's basically the same calculation, but at the next level of abstraction. And we probably will have to further work on it, kind of trying to make it at a higher and higher level. So here maybe one observation. For all this machinery to work, so we start with L, or if you want, with curly L, in defining our classical fields theory. But then, at this stage, we also need to add, or we need to find the structure gamma. It turns out that in the setup that I showed you today, gamma is unique under some conditions. And that's the topic of the exercise 4. But in more complicated field theories, gamma may not be unique. In this case, if gamma is not unique, then maybe you should modify the definition of your field theory and say that you start with a pair L gamma such that delta L minus d gamma would be of some nice form. Right? So here it was like our definition was rather economic, but maybe in field theories with high derivatives you probably need to add this gamma. So gamma, so it's a kind of hidden part of the definition. So actually our definition perhaps in a more abstract context wouldn't fly if we didn't choose the gamma. So possibly part of definition. Right. So as I said, today we introduced the main players in the classical field theory game, and we even were able to upgrade one of our calculations to the next differential geometric level. So what we do next time, you already had discussion of the Nussert's theorem and symmetries in classical mechanics, and it is roughly the same, but still there is more freedom, so there will be more examples on the one hand, and on the other hand we'll discuss more the structure of the space of solutions of the equations of motion, of the Euler Lagrange equations, and we'll make a contact to the symplectic geometry course. All right, so that's it for today.